Hello everyone, and welcome to my talk, Engineering Under the Watchful Eyes of Over 500,000 Hackers, Secure Coding Practices at HackerOne. My name is Sijbrandij, and I'm a Senior Software Engineer at HackerOne. We have engineering teams in Groningen, the Netherlands, and San Francisco, where I'm based. I came up with the idea for this talk in conversations with colleagues about our experiences when joining HackerOne and what we learned about secure coding. Personally, after joining HackerOne and learning about how we promote secure coding and ensure platform security, I was surprised about the amount of things I learned, and I remember thinking to myself, why wasn't I aware of this before? Why didn't I learn about secure coding sooner? And why doesn't this topic get more exposure at conferences? I think since joining HackerOne in 2017, awareness of the importance of writing secure code has grown, but finding concrete examples of how teams approach this topic can still be difficult. So I figured I'd share the methods HackerOne has implemented to both promote secure coding and ensure platform security. First, I'll start by giving you a little bit of context about HackerOne and the market we operate in. HackerOne partners with the global hacker community to surface the most relevant security issues of our customers before they can be exploited by criminals. We provide an easy-to-use, all-in-one platform to hackers and customers. To date, we have paid out over $100 million worth of bounties to hackers worldwide. Our customers are organizations that range from open-source projects to government and for-profit organizations in all imaginable sectors and sizes. Our customers can choose from different types of programs, such as vulnerability disclosure, bug bounty, and pen tests. Our platform serves the entire process of vulnerability disclosure, from submission of the vulnerability to communicating internally and with the reporter, integrating the customer's issue trackers, and paying the reporter for the vulnerabilities they found or the work they did on a pen test engagement. This means that our platform contains a lot of sensitive, critical, and potentially valuable data, most notably vulnerability reports that have been submitted to a customer but haven't been resolved yet, and PII on the hackers, like their identity, financial, and tax information. As a result, we are a target, both hackers who want to make sure we are secure and not vulnerable, as well as criminals who want to get to those undisclosed, unresolved vulnerabilities. So we have a lot to secure if we want to succeed in our mission to make the digital world safer. The practices I'll be sharing concern mostly this part of our tech stack. We do use more technologies at HackerOne, but these are the ones I'll be talking about today. We host our website on AWS. We use a Postgres database. We retrieve information from the database using Apollo and GraphQL. And our front end is written mostly in React, and our back end is written in Rails. So let's get to those secure coding practices. Even though your stack might differ from ours, you should be able to map the concepts behind our practices to your stack. I've organized our practices according to the different stages of the DevOps lifecycle, and then there are a couple of miscellaneous methods that didn't really fit any particular stage, but were worth a mention. In the planning stage, our practices are mostly focused around thinking critically about the feature we're building. When discussing the technical implementation, we think through all possible side effects of the proposed change. We have a security team which is available to help conduct a security architecture review. The review is pretty structured, so after doing a security architecture review a couple of times, it becomes easier to ask the right questions yourself. At HackerOne, most engineering teams allow every engineer, regardless of their seniority, to technically lead a project, so all engineers get exposed to the security architecture review process. Another aspect of the planning of a project entails defining who should be able to have access to the data and who should be able to perform an operation on that data. I'll discuss what we do with that information in the next phase. In the coding phase, we explicitly name unsafe methods. This makes it easy for the engineer to identify potentially dangerous methods and encourage them to use an alternative, more secure method. When an engineer uses such a potentially unsafe method, their merge request will receive more scrutiny from reviewers during the code review process. So, to speed up their work, engineers are encouraged to think about how they can achieve the same result without using potentially dangerous methods. Second, we operate using safe defaults. An example of that is that in our service layer, a user is unauthorized by default. The engineer has to explicitly authorize a user. It is always better to forget to authorize a user than it is to accidentally forget to restrict authorization. How do we handle that authorization, you may wonder? We use ACLs or access control lists for this purpose. In our implementation, we have an ACL class for each model in our application, which defines the conditions under which the requester is allowed to perform the requested action. By default, each method in the class will return false. This is an example of the safe defaults principle. So, unless there is a condition that the requester meets, the requested action will not be authorized. Also, the order of the conditions is significant. If condition A is met, it will return the value specified in the return X if method. So in this example, even though the vulnerability might be public, if there is no current user, the can comment method will return false. When a user makes a call to perform an action that is subject to authorization, the request is routed to an interactor. The interactor handles validation and authorization. The authorized method calls the ACL and passes it the record and the user requesting the action. The ACL will return either true or false, and if the ACL returns true, and assuming the validation returns true as well, the interactor calls a command. The command is the piece of code that actually performs the action. Splitting the code in this way makes the validation and authorization very explicit. It also allows for the creation of interactors that combine different commands that require maybe a different authorization given that combination. Second, we use a protector pattern to determine which attributes of the record the user has access to. A protector consists of role definitions and definitions of attributes that the role or group of roles has access to. A role definition is a scope on the active record model. To avoid duplication, it is possible to import roles from other protectors by joining the association on the model. This makes the roles defined in the associated model's protector available here. If the record in question is included in the collection returned by the active record scope, the attributes associated to that role will be available. So in this example, the scope definitions are shown on the left. On the right, in protected vulnerability, we have two role definitions that use the scopes defined in the vulnerability model, and we're importing the vulnerability_manager role from protected program using the copy roles method. Then we define the access to the attributes of vulnerability. In this case, the attributes ID and title are available to any user and vulnerability that satisfy any of the conditions in the group. So they're available for any vulnerability manager, any reporter, and any publicly disclosed report. However, the issue tracker reference ID is only available to vulnerability managers. Anyone else trying to query that attribute will get a nil response. The ID attribute is special here, since it determines access to the entire record. So if we would define a role that requires a logged-in user and add it to the group in protected vulnerability, any unauthenticated user will not be able to access any vulnerability record. A benefit of this strategy is that testing access to attributes becomes very explicit. It becomes easier to spot problems in access since you can test all the roles and what attributes are allowed and not allowed. Another benefit is that when we're creating queries on our front end, we can trust in our protectors to not return any records or attributes that the logged-in user does not have access to. The downside of this strategy is that we do have to check for and gracefully handle null objects in our front end. But considering that we have hackers that have automatic scanning of our GraphQL schema set up, we are happy to deal with those null cases. Using feature toggles to hide pages from view until they're ready is something that is not an uncommon practice. However, at HackerOne, we also use these feature toggles to hide data and restrict authorization through using them in our ACLs and protectors. In the ACL, shown on the left, we can check whether a feature toggle is enabled for a program or a user. In the protector shown on the right, we can create scopes for programs or users that have the feature enabled, thus restricting access to the entire object for users or, in this example, programs for which the feature toggle is not enabled. In our build step, we use a variety of linters, analyzers, and scanners to automatically detect problems in our codebase. Most technologies will have similar static code analyzers and scanners to help you identify potential issues. If the merge request fails a linter, your build will be red and you will have to fix the error before you'll be able to merge your code onto the release branch. We also run automatic auditors both for Rails and JavaScript to identify any packages that are known to have security vulnerabilities. Personally, I'm subscribed to a mailing list where Rails maintainers will publish any security vulnerabilities and remediation options. When I receive such an email, I know that my builds running at that moment will fail and nothing can be released until we update the vulnerable libraries. By basically blocking the ability to merge code onto the release branch when any analyzer, scanner, or auditing tool fails, we encourage engineers to fix the issues as soon as the problem is identified. We have a couple of bots configured in GitLab that will add labels, tag specific people, and add comments on merge requests if the merge requests contain a change that may cause security issues. By automatically tagging merge requests and setting up boards using those labels, we can make sure that those merge requests are visible to the people who have subject matter expertise and can be intercepted if they are deemed to be too risky. We also use a tool called Renovate, which will automatically create merge requests to upgrade any outdated dependencies. The merge requests are randomly assigned to an engineer for review and release. This ensures that we are always using the most up-to-date patch level of our dependencies. In our release stage, we'll revisit the security review process. During the coding phase, the implementation may have changed, so it is important to go back and assess the security implications of the feature as it was built. We also sometimes use the feature toggles here to roll out the new feature to a couple of hackers so they can test whether the new feature has any security vulnerabilities before we globally release the feature. We deploy our code using a Slack plugin called Nile. The plugin allows for every engineer in our team to deploy code without the need to give every engineer access to production servers. The benefit of this approach is that by having less engineers with access to production servers, the access to sensitive data is greatly reduced. The downside of restricting access to production servers is that debugging issues reported by users is more difficult because you can't just log in and inspect the data. We have two mitigations for this issue, which I'll tell you about in the next stage. As I mentioned before, to get around the issue of not having access to production servers, we have two tools. The first is a looker database with a user interface to inspect production data, either visually or by writing SQL queries. We are able to control the way in which our production data is mapped to the looker database, which is a copy of our production database according to the mapping strategy specified. In this example, when querying programs, we'll be able to see the values of all columns of the program's table. For vulnerabilities, we'll be able to see the values of most columns on the vulnerabilities table, but we're only able to see whether there is a value in the title and description columns, which contain extremely sensitive information. For users, we'll get an error when trying to query email addresses from the users table because that column won't exist in Looker. And when trying to query the bank accounts table, we'll get an error that the table simply does not exist. The benefit of this strategy is that we still have access to production data, and we are able to control how that data is represented. For instance, we can show attributes of a vulnerability that are not considered sensitive information, and summarize or drop any columns that do contain sensitive information. In 99.9% of the cases, the information available in our Looker database is enough to debug an issue. An added benefit of using this strategy is that we can create dashboards about the performance of the platform and visualize any business information without having to worry that people can get access to data that they don't need to do their jobs. The second tool we use to make up for the lack of access to production servers is production requests. Engineers are able to submit requests to the production servers, which are basically pieces of code as you would execute them in the Rails console. The requests are required to be peer-reviewed by another engineer. If you accidentally try to accept your own request, this will be denied and logged. To submit a review, you have to provide a link to an issue or write a description to provide more context around the reasons behind the request. We also save the author of the request and the person who accepted it. The reviews are pretty critical. One time I accidentally was printing sensitive information that I didn't need for the purpose of the request, and I received that feedback and my request was rejected. Once the request is accepted, the request will run in a job in a specific queue, and you'll see the output from your code and a backtrace in case there was an error. The benefit of this approach is that there is an easy way to find a log of operations executed on the database that are manually triggered by engineers with links to contextual information. This log is also useful when trying to explain any data discrepancies and to perform one-off operations. The downside of this method is the risk that engineers will use this tool to provide operations that should be codified. As engineers, we all have a responsibility to keep each other accountable, to not use this tool to cut corners or accidentally expose information that is not necessary for the task at hand. Other strategies we use in the operation phase is running daily web vulnerability scans using Detectify and Qualys. We also use Nessus to scan our database for vulnerabilities. Additionally, we use AWS Inspector to scan our servers for outdated packages. On top of all of this, we run a public bug bounty program, allowing our global hacker community to search and find vulnerabilities in our platform. Despite having so many security measures in place, hackers still find and report vulnerabilities. Since November 2013, hackers have found approximately 700 valid vulnerabilities, and our bug bounty program has paid out almost $400,000 worth in bounties. We also have run a pen test on our platform to have pen testers check our assets for the most common vulnerabilities as identified by the Open Web Application Security Project, or OWASP for short. This is a great addition to our bug bounty program because it directs the attention of the pen testers to specific assets and specific types of vulnerabilities to make sure those assets and vulnerability classes are covered, something that can't be ensured by the bug bounty program because we do not control where hackers focus their attention. In the monitoring phase, we have passive monitoring in the form of log collection to aid in incident response situations. We also have active monitoring in the form of sumo logic alerts based on the logs. For example, we have alerts set up when we detect a slow query. Identifying slow queries and fixing them prevents us from being vulnerable to denial of service attacks. Our security team reviews our audit logs to identify any anomalies in sumo logic logs on a weekly basis. They also perform weekly reviews of the results from vulnerability scans in the operating phase. So that would be results from Detectify, Qualys, Nessus, AWS Inspector, etc. Some other strategies we use to ensure platform security that don't really fit into any phase include having all vendor tools, for example, GitLab, Nile, Looker, etc., vetted by our security and compliance teams. Part of the requirements for tools used by HackerOne is having a vulnerability disclosure program and not having any currently unresolved vulnerabilities. It is not uncommon for our team to identify vulnerabilities during this vetting phase, and we won't implement that tool until those vulnerabilities are resolved. Another thing to consider is that frameworks such as React and Active Record, or Rails, prevent certain vulnerability classes as well. For example, let's say we have a comment model with a message attribute. If you want to show the value of the attribute in your front end, Rails' default is to assume that the string is not HTML safe and that it could contain executable code. Let's say the field contains Markdown. You'll have to explicitly tell Rails to treat that string as safe to render as HTML for it to show the text with the correct formatting. Again, an example of using safe defaults. Last, code review is mandatory at HackerOne. No engineer at HackerOne, whether they've joined the company 1 month or 6 years ago, is allowed to merge code into our release branch without a peer review. I would like to leave you with the following takeaways. Number 1, safe defaults are a great way to prevent any unwanted authorization issues. It is always better to not show data or not be able to perform an action than it is to have too much access to data and data altering actions. Think about how you can implement more safe defaults in your platform. Second, static code analyzers, automatic auditors, and scanners are a great way to identify any packages that have known security vulnerabilities, or identify patterns that are prone to security vulnerabilities. Make sure you have an easy, ideally automatic way to keep your packages up to date. Third, make secure coding the easiest option for engineers. By making security very explicit in your code, it will be easier for reviewers to identify problems, and it will help engineers to write more secure code by default. Lastly, the creativity of hackers and pen testers cannot be underestimated, and I highly recommend everyone to have at least a vulnerability disclosure program posted on your website, and ideally running a public bug bounty program or having periodic pen tests conducted on your application. Here at HackerOne, we are happy to help you find the best option for your organization. Thank you for your time and attention. I hope my talk has given you some ideas on what you can do to increase the secure coding practices and ensure platform security at your organization, or how you can write more secure code. If you want more information on vulnerability disclosure programs, bug bounty, or pen tests, you can find more information on our website, HackerOne.com. If you have any questions, feel free to contact me on Twitter at Sijbrandij.